potential energy. The graph shows us two salient properties. One is the potential energy is always negative. That's just a choice of our constant that we added. It becomes closer to zero. It increases towards zero as one gets farther from Earth, so it approaches zero at infinite distance from Earth. Near Earth, it increases. MGH and minus GMM over R are not the same, but if one shifts this down by an appropriate constant, then one sees that as long as h is much smaller than the radius of the Earth, you get a good approximation. The statement oft heard that there is no gravity in space, we've seen is patently false. The Earth's gravitational attraction extends throughout the universe, but it does weaken with distance. And so perhaps a corrected version that sometimes one hears is that astronauts in the space station are weightless because the gravitational force of Earth is weaker at larger distances from the center of the Earth. Here we see Stephen Hawking weightless. No. The space station, as we have said, orbits at an altitude of about 400 kilometers, so we can compute the force of gravitation, we can compute the weight of an object, say myself or even Hawking, at an altitude of h above the Earth. We found that the approximate version for the force of gravity for altitudes h smaller than the radius of the Earth is this formula. This makes it easy to plug in the numbers, and you find that in the space station, your weight is in fact 87%. In other words, the force with which the Earth attracts you is 87% of what it would be on Earth. Why then are astronauts weightless in the space station? Why is Hawking weightless in this picture? Stephen Hawking is far too important to humanity to allow him to travel to space and take the risks of real space travel. Hawking is weightless because in fact he is accelerating towards the ground with an acceleration that is essentially g. When you are in free fall, there is no gravity, and there's a beautiful demo that explains this. We said that all you have to do to be weightless is be in free fall. So what I'm going to do in this demonstration is I'm jumping off a box. I'm jumping in ultra slow motion because we filmed the video with a high-speed camera and have slowed it down further. And as I fall, to demonstrate that I'm really weightless, I'm dropping this little white ball. And what you see is that as I drop the ball, of course the ball's falling, so am I. To my eyes, the ball is hovering in front of my face and it's not moving. And it won't stop falling in concert with me until my feet hit the ground. You can tell exactly the moment when my feet hit the ground, because that is the moment when the ball is no longer level with my nose. Well, I hope you found that amusing. What we saw is that when you are freely falling, you experience no gravity. A ball you drop will hover in front of your face. Had I thrown that ball up, it would have, relative to my nose, moved up at a constant velocity. And this is important because in space there are no floors for your feet to hit, and so everything is in free fall. For example, the Earth, as it orbits the Sun in its circular motion, is in free fall under the gravitational influence of the Sun, which means that when studying the motions of objects near Earth, we can completely ignore the Sun's gravity. We are all in free fall towards the Sun. Really? Almost. The reason we are only almost all in free fall towards the Sun is because we're all actually held together by staying on Earth, so we're all falling towards the Sun with one constant acceleration, and that could not possibly be the free fall acceleration towards the Sun at all the positions we are, because at different positions, the free fall acceleration towards the Sun is different, depending on your distance from and direction to the Sun. These differences in the gravitational free fall acceleration at different points of an extended object will lead to forces, tidal forces, we'll see why we call them tidal forces, that account for the differences in gravitational acceleration between different parts of an object. These differences manifest themselves in leftover gravitational forces. Like all gravitational forces, they are proportional to your mass. So the tidal force on a refrigerator is more than the tidal force on a tennis ball, and they're given by your mass times the difference between the gravitational acceleration towards, say, the Sun, where you are, and the acceleration with which, as a denizen of Earth, you actually are falling onto the Sun. That would be the gravitational acceleration towards the Sun as it applies at the center of the Earth. This sounds a little bit confusing, and like many things, can be clarified by a good calculation. Let's turn to that. Let's do this And let's do the calculation. So in this image, we have the Earth over here. The sun, I'm going to assume, is way over there in the left-hand corner and way outside the image. And because the sun's gravitation applies a force to the Earth, given by F equals g times the mass of the sun, divided by the distance to the sun squared times the mass of the Earth, the entire Earth is accelerating to the left towards the sun with an acceleration given by this is equal to the mass of the Earth times the acceleration of the Earth, and I can, as always with gravity, cancel the factors of the mass of the Earth. And so what I find is that the entire Earth is accelerating towards the sun with this acceleration, where the distance to the sun I'm going to take as always as the center-to-center distance, because that is what Newton taught us to do with spherically symmetric objects. Now, the important thing is the entire Earth is accelerating to the left with this acceleration, and because this is the acceleration of free fall, gravity would cancel, except that if you are sitting at this point on Earth, you are a little bit nearer the sun than the center of the Earth by a very small amount. This is 6,400 kilometers. The distance to the sun is 150 million kilometers, but it's a difference nonetheless. So the gravitational acceleration towards the sun here is a little bit larger. And so the gravitational acceleration towards the sun at this point is larger because you are closer to the sun. Indeed, the denominator for computing here should be decreased by the radius of the Earth. Similarly, the gravitational acceleration on the far side of the sun will be smaller than the value in the center of the Earth because you're at a larger distance by the radius of the Earth. Now, the radius of the Earth is, of course, much smaller than the distance to the sun. This gives us a wonderful opportunity to apply our approximation that we learned from Newton. We do the usual steps. We write here, pull out d squared. I'll shortcut the next step. We will get 1 minus r radius of the Earth over distance to the sun to the power minus 2. X is the small quantity, radius of the Earth divided by distance to the sun. A is negative 2. And the result is gm over d squared, which is simply A, and then times 1 plus 2 r over d. And so this is our approximate value, valid because the Earth is much smaller than the distance to the sun, for the value of the acceleration of gravity on the near side to the sun. And we can make a similar calculation over here. The difference will be this plus sign will turn into a minus sign when we multiply it by minus 2. So we can write the acceleration over here in a similar form. Now this suggests rewriting this as a sum of two terms, the acceleration with which the Earth approaches, and then an extra little bit. So an object over here has a free fall acceleration towards the sun that is larger than this one by the amount of this little yellow arrow, which signifies A times 2r over d. And similarly, an object on the far side of the sun has a gravitational acceleration towards the sun that is less than the acceleration with which the Earth moves towards the sun by approximately the same amount to this order of approximation. Now, one can apply a similar logic to these positions on Earth. Their distance from the sun to first order is the same as that of the center of the Earth. So one asks, why is the gravitational acceleration here different from that at the center of the Earth? Well, that is because, to a very small extent, the direction from here to the sun is not the same as the direction from here to the sun, as these arrows, in again a grossly exaggerated version, demonstrate. This would have the sun about here. The sun should be very far, so this angle should be tiny. But again, I can rewrite these as the gravitational acceleration at the center of the Earth plus a small correction. And so the net result is that the gravitational acceleration with which the Earth is moving towards the sun, that part of the sun's gravity is cancelled by the Earth's motion. But the leftovers, these yellow little differences, are not cancelled. So if I put those differences back in their place, I see that the net result is that the sun exerts a small force upward away from Earth on this side of the Earth, and a small force upward away from the Earth on this side of the Earth, and a small force downward on this side of the Earth. In other words, the sun is doing its best to smush the Earth into this oval that is elongated in the direction of the sun. And so, of course, the Earth is kind of a rigid object. The sun cannot manage to deform the Earth, but the Earth is under some kind of tidal stress. Now, before we get too excited, let's figure out how strong this force is that we've calculated. Again, the magnitude of the force depends on what it's acting on. These are all accelerations. So imagine a 1 kilo rock and figure out the net force that this has, or better yet, compute an acceleration and compare it to the acceleration of gravity. So we know, is this rock essentially rendered weightless? Is it lifted off the Earth by these tidal forces? So we can do the calculation. We have here all the quantities we need. The tidal acceleration due to the sun is the difference, that little yellow difference, which was 2gm over d squared times r over d. The salient point is that because I have 2gm over d squared times r over d, this decreases with distance from the sun like the third power of distance. Remember, the gravitational force itself decreases like the second power. And I want to compare this acceleration to something I know, so I will do the usual scaling trick that I like to use. We'll try to pull out a factor over here of the mass of the Earth divided by the radius of the Earth squared. I didn't have the mass of the Earth, I had the mass of the sun, so I get one factor here. I had the radius of the Earth divided by the distance to the sun cubed, so I get a scaling factor. Notice I have an acceleration that is known. This is our friend g. These are dimensionless factors, so I'm relating an acceleration to an acceleration. And plugging in the ratio of the sun's mass to the Earth's and the cube of the ratio of the Earth's radius to the distance to the sun, I find that the acceleration, the tidal acceleration due to the sun, is very small. It's 5 parts in 100 million, the acceleration of gravity. So no, it is not about to rip the Earth apart. This is the tidal acceleration due to the sun. What else might exert a tidal influence on the Earth? Well, the second object that we might imagine would be the moon. Now, the moon is much less massive than the sun, but it is closer. And so, because of this third power of the distance, one might imagine that the tidal force generated by the moon might be comparable to that generated by the sun. And indeed, a simple scaling argument tells us that to get the tidal acceleration due to the moon relative to that from the sun, I multiply by the ratio of the masses and the ratio of the distances to the power -3. Plugging all the numbers in, I find